carbohydrates, how they're digested, how they're absorbed, and really what your body's doing with them. That's what we're going to take a look at in this video. Carbohydrates. When you start the digestive process, you're starting in the mouth. You're starting with both mechanical and chemical digestion. Now, the mechanical is going to be physically chewing the food. Sure, you're chewing it, you're mechanically breaking it down. Your teeth are grinding it up into smaller pieces. But the chemical side of things, that's utilizing enzymes. Now, in this case, we're looking at your saliva, salivary amylase. So your salivary glands in your mouth are going to secrete this salivary amylase. Now, ASE means enzyme. So this salivary amylase is going to help to break down, or I should say start to break down, disaccharides, oligosaccharides, as well as starches. Now, I'm saying it's only starting because for starches, for example, you're only breaking down maybe about 5% of those starches that you're ingesting and eating. So it takes a bit more as you get lower into the GI tract. The mouth is just a starting point. So you take that, you chew up your food. Now, as you chew and you swallow, you're swallowing down the esophagus, no real digestion occurring there, into the stomach. Once you get in the stomach, now you're going to start to churn and mix up that food that you started to chew up and digest. The stomach will mix with hydrochloric acid, HCl, as well as starting to churn and mix and give a little bit of mechanical digestion there as well. So what's happening now is we're creating what's called chyme. This is this homogeneous mixture of the food that you chewed up, as well as the different enzymes and juices that are mixed in the stomach. So you're kind of mixing this all together. But then your stomach can't really break it all down, so it has to send it off to the small intestines. But it only sends a little bit at a time. We're talking on the milliliter side of things, just a couple milliliters. As it does that, it sends a little bit into the small intestines. In the small intestines, it's not as acidic, so the hydrochloric acid is pretty much neutralized. What happens instead is your pancreas is going to secrete pancreatic juices, which contain enzymes. Now, these enzymes are able to break down all the macromolecules, but we're only focusing on the carbohydrate right now. So we're looking at our pancreatic amylases. They're going to help to break down the carbohydrates in the small intestines. But your intestines also are going to have their own secretions. The cells lining the walls of the small intestine, they'll be able to secrete some enzymes to help out also. So what we're secreting are things like maltase, sucrase, lactase, and just like the names imply, those enzymes break down the carbohydrates they're named for. So lactase breaks down lactose. Sucrase breaks down sucrose. Maltase breaks down maltose. Let's go back to that lactase for a second though. Now, some individuals are going to be lactose intolerant, but that has a huge range. You might be just a little bit intolerant or severely intolerant. That's all dependent usually on how much of the enzyme lactase your body produces and secretes. The reason that's an issue though, because just not breaking down the sugar, that doesn't really harm you. The issues come in because you don't break down the lactose in the small intestines and it reaches the large intestines. By reaching the large intestines, the bacteria that are found there, and again, there's healthy bacteria in your large intestines. They should be there. But those bacteria then will start to break down the lactose. That's where the symptoms of lactose intolerance can come from. The bacteria in the large intestines are releasing gas, releasing irritants, and that can cause all of the problems with lactose intolerance in individuals. So it's all based on that enzyme, that lactase enzyme. Now, as you break these down, remember, we're breaking these disaccharides down to monosaccharides. So for example, that sucrase will break down sucrose into glucose and fructose. So those individual monosaccharides then can be absorbed by the small intestines. Because really, for digestion, the small intestines is where you pull things into your body. It's where you absorb them into your blood. So in the case of carbohydrates, absorption, we're looking at the actual cells of the small intestines having these transport proteins. The transport proteins can help to move the broken down pieces, those monosaccharides, things like glucose, galactose, fructose. It can move those into the bloodstream. Now, once in the bloodstream, the first stop is the liver. All of your blood that's collected from around the GI tract heads to the liver for cleaning and processing. So the liver is going to take your galactose, because it's not the most stable in the world, and convert it into glucose. Well, that glucose then can be a great source of energy, or it can be sent to other cells to be stored for future use. Fructose is going to be broken down to smaller and smaller pieces, because fructose is really more helping glucose be uptaked and absorbed into the liver. Or the liver might simply just say, you know what, I'm going to store glucose. I'll keep it here for future purposes. Because maybe you want to have reserves. Make glycogen. Maybe you're all set and say, you know what, send it out to the muscle cells, let them store it. Or send it out to other cells and let those cells run it through the entire process of making ATP. So your liver is the first stop. Now, once the blood levels of glucose are sent out, so your liver is sending glucose out, the levels of glucose are very carefully monitored. You don't want too much or too little. So what's happening here now is your body's going to either secrete insulin, hormone, or glucagon, a hormone. So let's say you just had a meal, just a nice big meal, you got plenty of glucose being absorbed in your GI tract. Your blood glucose levels are elevated. That means insulin is being secreted. Insulin is going to help reduce blood sugar levels. It'll trigger your cells to uptake more glucose and either make energy out of it, ATP, or simply store it. But let's say you haven't eaten in a while now, and it's been a bit, and your body is starting to get a little hungry. Then the blood glucose levels would be falling, getting lower. In this case, you have glucagon being secreted. Again, glucagon is a hormone. The glucagon will help to stimulate the release of glucose from the stored tissues. So the liver, for example, will be breaking down its glycogen and releasing glucose into the blood, trying to make sure you maintain a certain level, the idea of homeostasis. This is all being done by negative feedback. All being done because there's a problem, too much or too little of glucose in the blood, which then tells your body, hey, we have to adjust this, we got to fix this. We can't keep these levels off. So it's helping to make sure that you're balancing out the amount of carbohydrates, specifically glucose, in your blood. Now, all these glucose molecules, all these carbohydrates that we're ingesting, the vast majority get absorbed, but not all. Remember, we have different dietary fibers that don't get absorbed, they pass on through. There are some restricted starches that just can't get absorbed, they pass on through. Now, the bacteria of the large intestines, again, they can come into play a little bit. They can help to break some down, but most of them will be passing through the GI tract and helping make sure our systems are getting cleared out. But those little bit that are being broken down in the large intestines, they can help with the large intestine cells gain a little bit of extra energy. Not much, but just a little extra boost there. All right, let's go back to that glucose in the blood, because we have what's called the glycemic index. Now, this glycemic index is measuring the effects of carbohydrates containing foods on your blood glucose levels. So you're thinking, well, yeah, that makes sense. If you have higher carbohydrates in the food you're eating, you have more glucose in your blood. Pretty much exactly, that's what it is. But the reason this is important is if you're trying to monitor how much you're taking in, so how many carbohydrates you're ingesting, the glycemic index can help you realize, you know what? This is going to have more of an impact compared to this. Because certain things, let's take, for example, fruits and vegetables. If they're overripe, like a banana, for example, you have bananas, you can eat them when they're a little green, you can eat them when they're a little yellow, you can eat them when they're brown spots. But when you get to that point of being very ripe with those brown spots, there's a lot more sugar in that banana than there previously was. The ripening process increases the sugars and makes more available to how we can absorb and digest them. So sometimes it makes a difference of how ripe something is, not just what the food is. So we're looking at low carbohydrate foods, low glycemic index, high carbohydrate foods, higher glycemic index. But again, taking into account how ripe it is, as well as taking into account, is it cooked? Cooking foods can help to make some of those insoluble or indigestible carbohydrates more digestible. It allows our bodies to be able to absorb more of them and take more in. So again, that cooking can alter the glycemic index of some foods also. So a lot of factors come into play here, not just this food has this rating, but how ripe is it? Is it cooked? Is it not cooked? And when you're talking about cooking, how much? Is it fully cooked, like been cooked for 15, 20, 30 minutes, or is it more like a blanching, where it's just a quick little, get it warm, just break it down a little bit? They all impact the glycemic index. So that is important if you're trying to track carbohydrates, and especially important if someone is diabetic. Because in the case of someone that is diabetic, they have to watch their glucose intake to make sure they don't have problems with too high or too low of glucose amounts in the blood. So there's a whole lot of factors that go into what that glycemic index is and how it impacts your blood levels of glucose. But one of the reasons why we have to make sure we monitor that level is because of energy production. Remember, glucose is the primary molecule that's being pulled into cell respiration. And all of our cells are going through cell respiration to produce ATP, adenosine triphosphate. So you go into glycolysis, then the citric acid cycle, and finally going into the electron transport chain. So hopefully that rings some bells from previous videos. If not, you might want to take a look back at that and refresh the idea of how the cell cycle is working there for cell respiration. Because you have to produce ATP for every cell to function to make sure that every cell has the energy it needs to either make new machinery or go about their daily tasks. But the one thing again, balance. You have to have enough glucose to power cell respiration. But if you have too much glucose, your body starts to store it as lipids. So again, there's that balance of storing glucose in glycogen, using glucose in the cell respiration cycle, or having an overabundance in general and it turns into lipids, fat storage. Because you want to have some storage. You want to have some glycogen. Because you're not constantly eating every minute of the day, so you have to have some reserve energy. But again, too much glycogen, if you go above those kind of upper limits of storage, which in general is about 4,000 kilocalories of glycogen being stored. And that's a lot of storage, by the way, 4,000 kilocalories. So that's plenty of storage. Of that 4,000 kilocalories, about 3,000 is stored in the muscles, and about 1,000 kilocalories is stored in the liver. So the muscles will use those when they have movement or any action in the future. The liver can send it out into the bloodstream, allowing for other cells to then absorb it and produce their own energy. But again, balance. Anything above that, give or take 4,000 kilocalorie level, is converted into lipids, which you have to have some lipids, that's healthy, but then too much lipid storage can become a problem. But glucose and carbohydrates, we keep talking about energy. They're not just energy. They're also building materials. Ribose and deoxyribose. Ribose is the sugar in RNA. Deoxyribose is the sugar in DNA. You also have some carbohydrates in your cell membranes. So there is a building component to carbohydrates as well. So you have to make sure it's not just all energy, but you're able to build these vital components of your cell machinery. So everyone's always watching out for carbohydrates, or sometimes they're kind of paying attention a little bit. But sometimes carbohydrates are the center focus of a particular diet. There are diets like the Atkins diet, the South Beach diet, called the Zone diet. Now, all of these diets are looking at restricting carbohydrate intake. They're all saying it's beneficial, it's healthy. Now, the problem is there's been a lot of research, but no one can really say it is healthy or is beneficial. For some individuals, it works. They can balance out. They figured out that point where, hey, I need this much carbohydrate and things stay healthy, but it's not as what the recommended levels might be. So if trying any of these diets, it's kind of important to also know what your body needs to make sure you're not shortchanging it on the glucose levels. But all of this glucose, all of this carbohydrate ingestion, if you ever looked at any product labels, food labels, and try to figure out how much they are processed, how much processing went into that food, it's not always apparent because they don't come out there and say these carbohydrates are processed. No. But what you can do is look at the ingredient list. If the ingredients are listed something like whole wheat, that's not much processing. But whole wheat flour would be more processing because it was broken down an extra step. It was processed into flour. Now, it's not saying that whole wheat flour is bad by any means, but that's an extra step of processing. If instead of whole wheat flour, it says white flour, or just flour, that could be then another step of processing. So you can start to get little indications by the list of ingredients of how much processing went into the food. But other things on labels you might see of, like sugar-free, for example. Well, according to the regulations, sugar-free simply means 0.5 grams of sugar or less per serving. So it's not really sugar-free. It's not much in there, but there still can be some. So that 0.5 or less is what's allowed to be called sugar-free. Other things you have are things like reduced sugar or a low sugar food. Both reduced sugar and low sugar, they're going to have 25% less sugar than comparable products. You're saying, well, why are there two different names? Reduced sugar means that item was processed to have less sugar. Low sugar means that item naturally had lower sugar than similar products, just based on the way it was made. So regardless, it's still lower in sugar, but how to get there is a question. That's the difference of reduced sugar, they're taken out or processed out, while low sugar, the whole process of making it just had less sugar in general. So understanding what these labels mean can help you understand the carbohydrates that are found in those components as well. So understanding and knowledge is a great thing. Until the next video.